What if everything you thought you knew about the universe was just the tip of the iceberg? Imagine staring into the night sky, only to realize that the stars and galaxies we see are just a fraction of what's truly out there. The cosmos is a place of endless mystery, filled with questions that even the brightest minds on Earth can't yet answer. From the invisible forces shaping the universe to the strange phenomena lurking in the depths of space, there's so much we don't understand. Today, we're diving into 25 of the biggest unanswered questions about space, questions that challenge our understanding of reality itself. Why does the universe expand faster than it should? What lies beyond the edge of the observable cosmos, and could there be life out there waiting to be discovered? These aren't just scientific puzzles, they're invitations to explore the unknown. So, if you're ready to embark on a journey through the greatest mysteries of the universe, stay with us. By the end of this video, you'll see the cosmos in a whole new light, and maybe, just maybe, you'll start to wonder what else is out there waiting to be uncovered. Let's begin. Now turning to our first question, what is dark matter? Imagine this: everything we can see in the universe, from the tiniest grain of sand to the largest galaxy, makes up less than 5% of the cosmos. The rest, it's something we can't see, touch, or even detect directly. This invisible substance is called dark matter, and it's one of the greatest mysteries in modern science. Dark matter doesn't emit, absorb, or reflect light, which is why it's so hard to observe. Yet we know it's there because of its gravitational effects. Galaxies spin faster than they should, and clusters of galaxies bend light in ways that can't be explained by the visible matter alone. Without dark matter, the universe as we know it wouldn't exist. But what exactly is it? Scientists have proposed several theories. Some think dark matter is made up of particles that don't interact with light or ordinary matter, while others suggest it could be something entirely different, like tiny black holes formed in the early universe. Experiments like the Large Hadron Collider and observatories like the James Webb Space Telescope are working tirelessly to uncover its secrets. Yet, despite decades of research, dark matter remains elusive. It's a reminder that even in our vast universe, some of the most fundamental questions are still waiting for answers. Now turning to our second question, what is dark energy? If dark matter is the invisible glue holding galaxies together, dark energy is the mysterious force pushing the universe apart. In the late 1990s, astronomers made a startling discovery. They found that the universe isn't just expanding, it's expanding faster and faster over time. This acceleration defied everything we thought we knew about gravity and the cosmos. The culprit, dark energy, unlike dark matter, which pulls things together with gravity, dark energy seems to work in the opposite direction, acting as a kind of anti-gravity that stretches space itself. But what exactly is it? Scientists aren't sure. One leading idea is that dark energy is a property of space itself, often referred to as the cosmological constant. This concept dates back to Albert Einstein, who introduced it to explain a static universe, a theory he later abandoned, but now it's back in the spotlight as a possible explanation for dark energy. Another theory suggests that dark energy could be a dynamic field that changes over time, known as quintessence. Whatever it is, dark energy makes up about 68% of the universe, dwarfing even dark matter. Yet, despite its dominance, we know almost nothing about it. The challenge lies in its invisibility. Dark energy doesn't interact with light or matter, making it nearly impossible to detect directly. Instead, scientists rely on indirect methods, like observing distant supernovae or mapping the large-scale structure of the universe. These observations help us measure the effects of dark energy, but they don't reveal its true nature. The implications are profound. If dark energy continues to drive the universe's expansion, it could lead to a future where galaxies are so far apart that the night sky becomes empty and dark. Or if dark energy changes over time, it could alter the fate of the cosmos in ways we can't yet predict. For now, dark energy remains one of the greatest puzzles in science, a reminder that the universe is full of surprises and that some of its biggest secrets are still waiting to be uncovered. Now turning to our third question, is there life beyond Earth? This is perhaps one of the most profound and tantalizing mysteries of the cosmos. For centuries, humans have gazed at the stars and wondered if we are alone in the universe. Today, science is closer than ever to answering that question. The search for extraterrestrial life spans a wide range of possibilities, from tiny microbes on Mars to advanced civilizations in distant star systems. Let's start with our own cosmic backyard. Mars has long been a prime candidate for hosting life, or at least the remnants of it. Missions like NASA's Perseverance rover are actively exploring the red planet, searching for signs of ancient microbial life in its rocks and soil. The discovery of liquid water beneath the Martian surface has only fueled hopes that life could exist there, even if it's just beneath the surface. But Mars is just the beginning. Beyond our solar system, the search for life extends to exoplanets, planets orbiting other stars. Thanks to telescopes like the James Webb Space Telescope, we're now able to study these distant worlds in unprecedented detail. By analyzing the atmospheres of exoplanets, scientists can look for chemical signatures that might indicate the presence of life, such as oxygen, methane, or even industrial pollutants. Some exoplanets, like those in the habitable zone of their stars, where temperatures could allow liquid water to exist, are particularly promising, but the search doesn't stop there. Scientists are also exploring the possibility of life in more extreme environments, like the icy moons of Jupiter and Saturn. Europa, one of Jupiter's moons, is believed to have a vast ocean beneath its icy crust, while Enceladus, a moon of Saturn, spews water vapor and organic molecules into space. These moons could harbor life forms that thrive in conditions very different from those on Earth. And then there's the search for intelligent life. Projects like SETI, the search for extraterrestrial intelligence, scan the skies for signals that could indicate the presence of advanced civilizations. While we haven't found any definitive evidence yet, the sheer size of the universe suggests that the odds are in our favor. With billions of galaxies, each containing billions of stars and planets, it's hard to believe that Earth is the only place where life has taken root. The implications of finding life beyond Earth are staggering. It would fundamentally change our understanding of our place in the universe and could even reshape our philosophies and religions. But for now, the question remains unanswered. The search continues, driven by curiosity, hope, and the belief that somewhere out there we are not alone. Now turning to our fourth question, what happens inside a black hole? Black holes are among the most mysterious and fascinating objects in the universe, regions of space where gravity is so intense that nothing, not even light, can escape. At the heart of every black hole lies the event horizon, the point of no return. Once something crosses this boundary, it's gone forever, at least as far as we know. But what lies beyond the event horizon? That's where things get truly mind-bending. The most widely accepted theory suggests that at the center of a black hole is a singularity, a point where matter is crushed to infinite density and the laws of physics as we understand them break down. Imagine squeezing the entire mass of a star or even a galaxy into a single, infinitely small point. It's a concept that defies our everyday experience and challenges our understanding of reality. But the mysteries don't stop there. Stephen Hawking proposed a groundbreaking idea known as Hawking radiation, which suggests that black holes aren't entirely black. Over incredibly long periods of time, black holes can emit tiny amounts of radiation and eventually evaporate. This discovery was revolutionary because it hinted that black holes might not be the eternal traps we once thought they were. However, detecting Hawking radiation is incredibly difficult as it's extremely faint and easily drowned out by other cosmic signals. studying black holes is no easy task. Because they don't emit light, we can't observe them directly. Instead, scientists rely on indirect methods, such as observing the effects of a black hole's gravity on nearby stars and gas. The first ever image of a black hole's event horizon, captured in 2019 by the Event Horizon Telescope, was a monumental achievement. It gave us a glimpse of the shadow cast by the black hole at the center of the galaxy Messier 87, but it also reminded us of how much we still don't know. One of the biggest challenges is reconciling the behavior of black holes with the laws of quantum mechanics and general relativity. These two pillars of modern physics seem to clash when it comes to black holes, leaving scientists with a puzzle that could reshape our understanding of the universe. For now, black holes remain one of the greatest enigmas in space, a cosmic riddle that continues to captivate and challenge us. As we move forward, the next question takes us even deeper into the unknown, exploring the origins of the universe itself. Now turning to our fifth question, how did the universe begin? The Big Bang Theory is the most widely accepted explanation for the origin of the universe, suggesting that everything we see today, stars, galaxies, and even space itself, began as an incredibly hot, dense point around 13.8 billion years ago. In a fraction of a second, this point expanded rapidly, setting the stage for the universe as we know it. But while the Big Bang Theory explains much of what we observe, it still leaves us with profound questions about what triggered this expansion and what, if anything, existed before it. One of the most intriguing ideas tied to the Big Bang is cosmic inflation, a theory proposing that the universe underwent an exponential expansion in the first moments after its birth. This rapid stretching would explain why the universe appears so uniform on large scales, but it also raises new mysteries. What caused inflation to start and stop? And what, if anything, lies beyond the boundaries of our observable universe? These questions push the limits of our understanding and hint at forces or phenomena we have yet to discover. Another speculative but fascinating concept is the multiverse. If cosmic inflation is correct, it's possible that our universe is just one of countless others, each with its own unique set of physical laws and constants. Imagine a cosmic landscape where universes bubble up endlessly, each one a separate reality. While the idea of a multiverse is captivating, it remains purely theoretical, as there's currently no way to observe or test for the existence of other universes. The Big Bang Theory also leaves us wondering about the very nature of time. Did time itself begin with the Big Bang, or was there something before it? If time did have a starting point, what does that mean for our understanding of cause and effect? These questions challenge not only our scientific knowledge, but also our philosophical perspectives on existence. Despite the progress we've made, the origin of the universe remains one of the greatest mysteries in science. The Big Bang Theory provides a framework, but it's a framework filled with gaps and unanswered questions. As we continue to explore the cosmos, we may uncover clues that bring us closer to understanding how it all began, or we may find that the answers lie beyond the reach of our current understanding. With the next phase of the journey in sight, we turn our attention to the ultimate fate of the universe, a question that ties directly to its origins. Now turning to our sixth question, what is the ultimate fate of the universe? Just as the Big Bang Theory attempts to explain the universe's beginning, scientists have proposed several theories about how it might end. These scenarios, known as the Big Freeze, the Big Crunch, and the Big Rip, paint very different pictures of the cosmos's final chapter, and each one hinges on the mysterious forces of dark energy and dark matter. Let's start with the Big Freeze, also known as the heat death of the universe. In this scenario, the universe continues to expand forever, driven by dark energy, the mysterious force accelerating its growth. Over trillions of years, stars will burn out, galaxies will drift apart, and the universe will grow colder and darker. Eventually, all that will remain is a vast, empty expanse with no energy left to sustain life or even motion. It's a chilling thought, but one that aligns with our current understanding of dark energy's role in cosmic expansion. Next, there's the Big Crunch, a dramatic reversal of the Big Freeze. In this scenario, the expansion of the universe slows down and eventually stops, pulled back by gravity. Dark matter, which makes up most of the universe's mass, would play a key role in this process. As galaxies and stars collapse inward, the universe would shrink back into an incredibly hot, dense state, a mirror image of the Big Bang. Some theories even suggest that this collapse could trigger a new Big Bang, creating a cyclical universe that expands and contracts endlessly. But for this to happen, dark energy's influence would have to weaken significantly, something we have no evidence for yet. Finally, there's the Big Rip, the most violent of the three scenarios. Here, dark energy doesn't just accelerate the universe's expansion, it grows stronger over time. Eventually, its force would overcome gravity, tearing apart galaxies, stars, planets, and even atoms themselves. The universe would end not with a whimper, but with a catastrophic shredding of space-time. While this might sound like science fiction, it's a real possibility if dark energy behaves in a certain way, though current observations don't yet support this extreme outcome. So, which of these fates awaits our universe? The answer depends largely on the balance between dark energy and dark matter, two of the most enigmatic components of the cosmos. Dark energy drives expansion, while dark matter provides the gravitational pull that could counteract it. Understanding their true nature is key to predicting the universe's ultimate destiny. For now, these theories remain speculative, but they remind us of the profound mysteries that still surround the cosmos. As we ponder the universe's end, we're reminded that its fate is deeply connected to its origins. And with that in mind, we turn to another cosmic mystery. Are there other universes out there? Now turning to our seventh question, are there other universes? The idea of a multiverse, a vast collection of universes beyond our own, has captivated scientists and philosophers alike. While it might sound like the stuff of science fiction, the concept of multiple universes arises from serious scientific theories, each offering a unique perspective on the nature of reality. One of the most intriguing theories is the idea of bubble universes. Imagine our universe as one bubble in a cosmic foam, floating alongside countless others. According to this theory, each bubble universe could have its own set of physical laws, constants, and even dimensions. These universes might exist in a higher dimensional space, completely separate from ours, making them impossible to detect directly. This idea stems from the concept of eternal inflation, where different regions of space stop expanding at different times, creating isolated bubbles of universes. Another fascinating theory involves parallel dimensions. In this scenario, our universe is just one layer of a much larger multiverse, with other universes existing alongside ours in higher dimensions. These parallel universes could be nearly identical to ours with only slight differences, or they could be wildly different, governed by entirely different laws of physics. Some theories even suggest that every possible outcome of every event exists in its own parallel universe, creating an infinite web of realities. But here's the catch: despite the compelling nature of these theories, there's no direct empirical evidence to prove the existence of other universes. The multiverse remains a speculative idea, supported more by mathematical models and theoretical frameworks than by observable data. This lack of evidence doesn't mean the multiverse isn't real, it simply means we don't yet have the tools or methods to test these ideas conclusively. The philosophical implications of a multiverse are equally profound. If other universes exist, what does that mean for our place in the cosmos? Are we just one of countless realities, or is our universe somehow special? These questions challenge our understanding of existence, purpose, and the very nature of reality itself. As we explore the possibility of other universes, we're reminded of how much we still don't know about the cosmos. And with that thought, we turn to another cosmic mystery. What are fast radio bursts and why do they remain one of the most puzzling phenomena in the universe? Now turning to our eighth question, what are fast radio bursts? These mysterious cosmic signals have baffled scientists since their discovery in 2007. Fast radio bursts, or FRB, are incredibly powerful bursts of radio waves that last just milliseconds, yet they release as much energy as the sun does in days or even weeks. Despite their brief appearance, these bursts have sparked a wave of curiosity and research, as their origins remain one of the most perplexing mysteries in astronomy. One of the most intriguing aspects of FRBs is their unpredictability. Some bursts are one-time events, while others repeat at irregular intervals. This inconsistency makes them incredibly difficult to study. Where do they come from? Theories range from highly magnetized neutron stars, known as magnetars, to collisions between dense objects like black holes or neutron stars. Some even speculate that these bursts could be signals from advanced extraterrestrial civilizations, though this idea remains highly speculative and lacks evidence. Recent discoveries have shed some light on these enigmatic signals. In 2020, astronomers detected an FRB originating from within our own galaxy, providing a rare opportunity to study one up close. This burst was linked to a magnetar, strengthening the case for these highly magnetic stars as a potential source. However, not all FRBs fit this explanation, leaving the door open for other possibilities. Advanced telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have played a crucial role in detecting and studying FRBs. These instruments are designed to scan large portions of the sky, increasing the chances of catching these fleeting events. As technology improves, scientists hope to pinpoint more FRBs and gather data that could finally unravel their origins. The mystery of fast radio bursts reminds us of how much we still have to learn about the universe. Each burst is like a cosmic whisper, hinting at processes and phenomena we don't yet understand. And as we continue to explore these signals, we're led to another fascinating question. Why is the universe expanding faster than expected? Now turning to our ninth question, why is the universe expanding faster than expected? This cosmic puzzle has left scientists scratching their heads, as the observed rate of the universe's expansion doesn't match the predictions made by our current understanding of physics. Known as the Hubble tension, this discrepancy has become one of the most pressing mysteries in modern cosmology. The story begins with the Hubble constant, a number that represents the rate at which the universe is expanding. Scientists have tried to measure this constant in two main ways. The first method looks at the cosmic microwave background, the faint afterglow of the Big Bang, which provides a snapshot of the early universe. The second method involves observing distant objects like supernova and galaxies to measure how fast they are moving away from us. The problem, these two methods give different results. The universe appears to be expanding faster today than what the early universe's data suggests it should be. This inconsistency challenges our understanding of fundamental physics. If the measurements are correct, it could mean that there's something missing in our current models of the universe. One possibility is that dark energy, the mysterious force driving the universe's accelerated expansion, is behaving differently than we thought. Perhaps it's growing stronger over time, or maybe there's an entirely new component of the universe we haven't discovered yet. Another idea is that our understanding of gravity might need an update, especially on cosmic scales. The implications of this mystery are profound. If the universe is expanding faster than expected, it could change our predictions about its ultimate fate. Will it end in a big freeze where galaxies drift apart forever, or could there be another unexpected outcome? As scientists continue to refine their measurements and develop new theories, the Hubble tension remains a tantalizing clue that our understanding of the cosmos is still incomplete. This question not only highlights the limits of our knowledge but also underscores the excitement of discovery. Every new observation, every refined measurement brings us closer to unraveling the secrets of the universe. And as we ponder this cosmic conundrum, we're led to another intriguing question. What are quasars and why do they remain such enigmatic objects in the cosmos? Now turning to our 10th question, what are quasars? These dazzling cosmic objects are among the most energetic and mysterious phenomena in the universe. Quasars, short for quasi-stellar radio sources, are the incredibly bright centers of distant galaxies powered by supermassive black holes. But what makes them so fascinating, and why do they continue to baffle scientists even after decades of study? At the heart of every quasar lies a supermassive black hole, millions to billions of times more massive than our Sun. As matter spirals into this black hole, it forms a swirling disk of gas and dust, heating up to extreme temperatures and emitting vast amounts of energy. This process makes quasars some of the brightest objects in the universe, outshining entire galaxies despite being relatively compact. In fact, a single quasar can emit thousands of times more energy than the Milky Way. Quasars are also time capsules, offering a glimpse into the early universe. Because light takes time to travel across vast cosmic distances, the light we see from quasars today actually left them billions of years ago. This means that by studying quasars, we're essentially looking back in time, observing the universe as it was when it was much younger. Quasars were especially common in the early universe, suggesting they played a crucial role in the formation and evolution of galaxies. Despite their importance, quasars remain shrouded in mystery. For one, we still don't fully understand how supermassive black holes which power quasars formed so quickly in the early universe. How did they grow to such enormous sizes in what seems like a relatively short amount of cosmic time? Additionally, the exact mechanisms behind the incredible energy output of quasars are still not completely clear. While we know that the accretion of matter plays a key role, the details of how this process works on such a massive scale remain elusive. Another puzzling aspect of quasars is their variability. Some quasars can change in brightness over surprisingly short periods, sometimes in just days or weeks. This rapid variability suggests that the regions emitting this energy are incredibly small, adding another layer of complexity to our understanding of these objects. Quasars also challenge our understanding of the universe's structure. Their immense brightness allows us to study the intergalactic medium, the gas and dust between galaxies, by observing how their light is absorbed as it travels through space. This has revealed a cosmic web of matter that connects galaxies across the universe, but it has also raised new questions about the distribution and composition of this material. As we continue to study quasars, they remind us of how much we still have to learn about the cosmos. These luminous beacons from the early universe not only illuminate the past but also challenge our present understanding of physics and astronomy. And as we delve deeper into their mysteries, we're led to yet another cosmic puzzle. How do stars form, and what secrets do they hold about the universe's evolution? Now turning to our 11th question, what is the true nature of time? Time is one of the most fundamental aspects of our existence, yet it remains one of the greatest mysteries in science. From the way we measure it with clocks to the way it shapes our perception of reality, time is both familiar and deeply enigmatic. But what exactly is time, and why does it continue to challenge our understanding of the universe? Albert Einstein's theory of relativity revolutionized our understanding of time, showing that it is not a fixed, universal constant, but rather a flexible dimension intertwined with space. According to Einstein, time can stretch and warp depending on gravity and motion. For example, time moves slower near massive objects like black holes or for objects traveling at speeds close to the speed of light. This phenomenon, known as time dilation, has been confirmed through experiments and is crucial for technologies like GPS satellites, which must account for these tiny time shifts to function accurately. But while relativity provides a framework for understanding time on a large scale, quantum mechanics, the science of the very small, paints a very different picture. In the quantum world, time seems to behave in ways that defy our everyday experience. For instance, particles can exist in multiple states at once until they are observed, and events can appear to happen in a different order depending on the observer. This has led some scientists to question whether time is even a fundamental property of the universe or merely an emergent phenomenon that arises from more basic processes. One of the most puzzling questions about time is its direction. Why does time seem to flow in one direction from the past to the future? This is known as the arrow of time, and it's closely tied to the concept of entropy, or the tendency of systems to move from order to disorder. While the laws of physics are mostly time-symmetric, meaning they work the same whether time moves forward or backward, our everyday experience tells us that time only moves in one direction. A broken glass doesn't reassemble itself, and we remember the past but not the future. But why is this the case? Is the arrow of time a fundamental law of nature, or is it a result of the specific conditions of our universe? Another intriguing idea is that time might be an illusion, a construct of our minds rather than a real feature of the universe. Some theories suggest that what we perceive as the passage of time is simply a way for our brains to make sense of the world, much like how a movie appears continuous even though it's made up of individual frames. If this is true, then the past, present, and future might all exist simultaneously, and our experience of time is just a slice of a much larger, timeless reality. The nature of time also has profound implications for our understanding of the universe's origins and fate. If time had a beginning at the Big Bang, what does that mean for the concept of before? And if the universe continues to expand indefinitely, could time eventually come to an end? These questions push the boundaries of both physics and philosophy, challenging us to rethink our most basic assumptions about reality. As we explore the mysteries of time, we're reminded that even the most familiar aspects of our existence can hold deep, unanswered questions. Time shapes our lives, yet its true nature remains elusive, inviting us to continue our journey of discovery. And as we ponder the flow of time, we're led to yet another cosmic puzzle. How do stars form, and what can they tell us about the universe's evolution? Now turning to our 12th question, how do stars form? Stars are the building blocks of galaxies, the engines that power the cosmos, and the source of the light and heat that make life possible. Yet, despite their importance, the process of star formation remains shrouded in mystery. How do vast clouds of gas and dust collapse to create these luminous giants? And what are the initial conditions that set this cosmic dance in motion? The journey of a star begins in the cold, dark regions of space known as molecular clouds. These clouds, composed mostly of hydrogen gas and tiny dust particles, are the nurseries of the universe. Under the right conditions, gravity begins to pull these particles together, causing the cloud to contract. As the cloud collapses, it fragments into smaller clumps, each of which can eventually form a star. But what triggers this collapse in the first place? Scientists believe that shockwaves from nearby supernova or the collision of molecular clouds could provide the necessary push, but the exact mechanisms are still not fully understood. As the cloud contracts, it heats up and the core becomes denser and hotter. When the temperature and pressure in the core reach a critical point, nuclear fusion ignites and a star is born. This process seems straightforward, but it raises many questions. For instance, why do some clouds form single stars while others create entire clusters? And how do the properties of the initial cloud, such as its mass and composition, influence the type of star that forms? One of the biggest mysteries in star formation is the role of magnetic fields. These invisible forces can either help or hinder the collapse of a molecular cloud, depending on their strength and orientation. Some theories suggest that magnetic fields can slow down the collapse, while others propose that they channel the gas into specific regions, accelerating star formation. Understanding the interplay between gravity, magnetic fields, and turbulence in these clouds is crucial to unraveling the secrets of star birth. Another unanswered question is how the first stars in the universe formed. These primordial stars, known as population 3 stars, were made almost entirely of hydrogen and helium, with no heavier elements to help cool the gas and facilitate collapse. How did these stars ignite in the early universe, and what were their properties? Studying these ancient stars could provide clues about the conditions of the early cosmos and the origins of the elements that make up everything around us. The formation of stars also has profound implications for the evolution of galaxies. Stars are not just luminous objects, they are factories that produce heavier elements through nuclear fusion and supernova explosions. These elements are then scattered into space, enriching the interstellar medium and providing the raw materials for new stars, planets, and even life. But how do the processes of star formation and feedback, such as stellar winds and supernova, shape the structure and dynamics of galaxies? This remains an active area of research, with astronomers using advanced telescopes and simulations to piece together the puzzle. As we explore the mysteries of star formation, we are reminded of the intricate and interconnected nature of the universe. Stars are not just distant points of light, they are the result of complex processes that have shaped the cosmos for billions of years. And as we continue to study these celestial phenomena, we are led to yet another cosmic enigma. What causes gamma-ray bursts, the most energetic events in the universe? Now turning to our 13th question, what causes gamma-ray bursts? These bursts are the most powerful explosions in the universe, releasing more energy in a few seconds than our sun will emit in its entire lifetime. Yet, despite their incredible intensity, the origins of gamma-ray bursts remain one of the greatest mysteries in astrophysics. Gamma-ray bursts are fleeting events, lasting anywhere from a fraction of a second to several minutes. They are so brief that catching them in action requires precise timing and a network of telescopes scanning the skies. When a burst is detected, astronomers race to pinpoint its location, often relying on satellites like NASA's Swift and Fermi missions. But even with these advanced tools, identifying the source of a gamma-ray burst is no easy task. One leading theory suggests that gamma-ray bursts are produced during the collapse of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses under its own gravity, forming a black hole. In the process, jets of particles are launched at nearly the speed of light, producing intense gamma-ray radiation as they collide with surrounding material. These events, known as long-duration gamma-ray bursts, are thought to be linked to supernova, the explosive deaths of massive stars. Another possible cause is the collision of two neutron stars. Neutron stars are the incredibly dense remnants of supernova, and when two of these objects spiral into each other, they can produce a short-duration gamma-ray burst. These collisions also generate gravitational waves, ripples in space-time that have been detected by observatories like LIGO and Virgo. The combination of gamma-ray bursts and gravitational waves offers a unique opportunity to study these cataclysmic events in unprecedented detail. However, not all gamma-ray bursts fit neatly into these categories. Some bursts defy explanation with properties that challenge our current understanding of these phenomena. For instance, why do some bursts produce afterglows, fading emissions at longer wavelengths while others do not? And what causes the incredible variability in the brightness and duration of these events? These questions highlight the complexity of gamma-ray bursts and the challenges scientists face in unraveling their secrets. One of the biggest obstacles in studying gamma-ray bursts is their immense distance. Most bursts occur billions of light-years away, meaning we are observing events that happened when the universe was much younger. This distance makes it difficult to gather detailed information about the environments in which these bursts occur. Additionally, the extreme conditions associated with gamma-ray bursts, such as intense magnetic fields and relativistic speeds, push the limits of our understanding of physics. Despite these challenges, gamma-ray bursts offer a unique window into the most energetic processes in the universe. They provide clues about the life cycles of massive stars, the behavior of matter under extreme conditions, and the evolution of the cosmos itself. As we continue to study these enigmatic events, we are reminded of the vastness of the universe and the many mysteries that remain to be solved. And as we delve deeper into the nature of gamma-ray bursts, we are led to yet another cosmic puzzle. What is the nature of neutron stars, the remnants of some of the most violent events in the universe? Now turning to our 14th question, what is the nature of neutron stars? These cosmic remnants are among the most extreme and fascinating objects in the universe, packing the mass of a star into a sphere no larger than a city. Born from the explosive deaths of massive stars, neutron stars are the dense cores left behind after a supernova. Imagine crushing the sun down to the size of Manhattan. That's the kind of density we're talking about. A single teaspoon of neutron star material would weigh billions of tons on Earth. The formation of a neutron star is a violent and dramatic process. When a massive star exhausts its nuclear fuel, its core collapses under its own gravity. The outer layers of the star are blown away in a supernova explosion, while the core is compressed into a neutron star. This process happens in mere seconds, but the result is an object with a gravitational pull so strong that it bends space and time around it. Neutron stars also spin incredibly fast, with some rotating hundreds of times per second, sending out beams of radiation that we detect as pulsars. But what lies inside a neutron star? This is one of the greatest mysteries in astrophysics. The intense pressure at the core of a neutron star is thought to crush matter into exotic states that don't exist anywhere else in the universe. Some theories suggest that the core might be made of strange quarks, particles that behave very differently from the protons and neutrons we're familiar with. Others propose that neutron stars could contain hyperons, another type of exotic particle. However, these ideas remain speculative, as the conditions inside a neutron star are impossible to replicate on Earth. Neutron stars also exhibit some of the strongest magnetic fields in the universe. These magnetic fields can be trillions of times more powerful than Earth's, creating environments where matter behaves in bizarre and unpredictable ways. For example, the surface of a neutron star is thought to be a solid crust of iron-like material, but beneath that crust, the intense pressure and magnetic fields could create a superfluid, a state of matter that flows without friction. This combination of extreme density, rapid rotation, and powerful magnetic fields makes neutron stars natural laboratories for testing the laws of physics under conditions we can't recreate anywhere else. One of the most intriguing aspects of neutron stars is their role in the universe. They are often found in binary systems where two neutron stars orbit each other. Over time, these orbits decay and the stars spiral closer together until they collide in a spectacular event known as a kilonova. These collisions are thought to produce heavy elements like gold and platinum, scattering them across the cosmos. They also generate gravitational waves, ripples in space-time that have been detected by observatories like LIGO and Virgo. By studying these events, scientists hope to learn more about the nature of neutron stars and the processes that shape the universe. Yet, despite decades of research, many questions about neutron stars remain unanswered. What exactly happens at their cores? How do their magnetic fields form and evolve? And what can they tell us about the fundamental forces of nature? As we continue to study these enigmatic objects, we are reminded of how much we still have to learn about the universe. And as we explore the mysteries of neutron stars, we are led to yet another cosmic puzzle. Why is there more matter than antimatter in the universe? Now turning to our 15th question. why is there more matter than antimatter in the universe? This is one of the most profound mysteries in physics, and it challenges our understanding of the very fabric of reality. According to the Big Bang theory, matter and antimatter should have been created in equal amounts during the birth of the universe. Antimatter is essentially the mirror image of matter, with particles that have the same mass but opposite charge. When matter and antimatter meet, they annihilate each other in a burst of energy. So, if equal amounts were produced, why does the universe today seem to be made almost entirely of matter? This imbalance, known as the matter-antimatter asymmetry problem, suggests that something tipped the scales in favor of matter during the early moments of the universe. Scientists believe that for every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny difference was enough to allow matter to dominate after all the annihilations took place. But what caused this imbalance? The answer lies in a process called CP violation, which refers to the violation of symmetry between particles and their antiparticles. In simple terms, the laws of physics seem to treat matter and antimatter slightly differently, but the exact mechanisms behind this are still unclear. Experiments like those conducted at the Large Hadron Collider are searching for clues by studying the behavior of particles and antiparticles. One leading theory involves hypothetical particles called neutrinos. Neutrinos are incredibly elusive, rarely interacting with other matter, but they might hold the key to this mystery. If neutrinos and their antimatter counterparts, antineutrinos, behave differently, it could explain why matter came to dominate. Another possibility is that unknown forces or particles existed in the early universe, creating conditions that favored matter over antimatter. The implications of solving this mystery are enormous. Understanding why matter dominates could reveal new laws of physics and shed light on the fundamental forces that govern the universe. It could also help us understand why galaxies, stars, and planets, and ultimately, life exist at all. Without this imbalance, the universe would be a very different place, filled with nothing but energy and radiation. As we continue to explore this cosmic puzzle, we are reminded of how much we still have to learn about the universe. And as we ponder the mystery of matter and antimatter, we are led to yet another question. What is the shape of the universe? Now turning to our 16th question, what is the shape of the universe? This is a question that takes us to the very edge of our understanding of space and time. The shape of the universe isn't just about its physical appearance, it's about its geometry, the way space itself is structured on the largest scales. Scientists have proposed several possibilities, each with profound implications for the nature of reality. One leading theory suggests that the universe is flat. In this scenario, space extends infinitely in all directions, and the rules of geometry we learn in school, like parallel lines never meeting, hold true on cosmic scales. A flat universe would mean that the total energy density of the cosmos is perfectly balanced, a delicate equilibrium that allows space to stretch without curving. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, seem to support this idea, but the evidence isn't conclusive. Another possibility is that the universe is spherical, like the surface of a giant balloon. In this model, space curves back on itself, meaning that if you traveled far enough in one direction, you might eventually return to your starting point. A spherical universe would imply that the energy density is higher than the critical value needed for a flat universe, causing space to curve inward. This would create a finite but unbounded cosmos, one with no edges but a definite size. Then there's the hyperbolic universe, a shape that's harder to visualize. In this scenario, space curves outward like the surface of a saddle. A hyperbolic universe would mean that the energy density is lower than the critical value, causing space to expand and curve in a way that defies our everyday intuition. In such a universe, parallel lines would diverge, and the geometry would be far more complex than what we're used to. Determining the true shape of the universe is no easy task. The vastness of space and the limitations of our observational tools make it incredibly challenging to measure cosmic geometry with precision. Even subtle distortions in the cosmic microwave background or the distribution of galaxies could hold the key, but interpreting these signals requires cutting-edge technology and a deep understanding of theoretical physics. The shape of the universe isn't just an abstract concept, it has real implications for the fate of the cosmos. A flat or hyperbolic universe might continue expanding forever, leading to a cold, dark future known as the Big Freeze. A spherical universe, on the other hand, could eventually collapse back in on itself in a big crunch. Understanding the geometry of the universe could help us predict its ultimate destiny. As we grapple with this question, we're reminded once again of how much we still have to learn about the cosmos. And as we ponder the shape of the universe, we're led to yet another mystery. What are cosmic rays and where do they come from? Now turning to our 17th question, what are cosmic rays? These mysterious high-energy particles constantly bombard Earth from space, yet their origins and how they gain such incredible speeds remain one of the great unsolved puzzles of astrophysics. Cosmic rays are not rays in the traditional sense. They're actually particles, mostly protons and atomic nuclei, traveling at nearly the speed of light. Some of these particles carry energies millions of times greater than anything we can produce in our most powerful particle accelerators. But where do they come from? That's the million-dollar question. Scientists believe that cosmic rays are accelerated by some of the most violent events in the universe, such as supernova explosions, the jets of active galactic nuclei, or even the collisions of galaxy clusters. These cataclysmic events can propel particles to unimaginable speeds, but the exact mechanisms behind this acceleration are still poorly understood. For example, how do these particles gain so much energy without being destroyed in the process? And why do some cosmic rays have energies so high that they defy our current understanding of physics? Detecting and studying cosmic rays is no easy feat. When these particles enter Earth's atmosphere, they collide with air molecules, creating a cascade of secondary particles. By the time they reach the ground, they've been transformed into a shower of lower energy particles, making it difficult to trace their original source. To overcome this, scientists use sophisticated detectors, both on the ground and in space, to study these showers and piece together the properties of the original cosmic rays. One of the biggest challenges is pinpointing the exact sources of these particles. Because cosmic rays are charged, their paths are bent by magnetic fields as they travel through space, making it nearly impossible to trace them back to their origins. This means that even if we detect a cosmic ray with an incredibly high energy, we might not know where it came from. Some of the highest energy cosmic rays, known as ultra-high-energy cosmic rays, are so rare and powerful that they've been dubbed "oh my god" particles. These particles carry so much energy that they shouldn't exist according to our current models of particle physics, yet they do. The study of cosmic rays isn't just about solving a cosmic mystery, it has practical implications too. These particles can affect satellite electronics, pose risks to astronauts, and even influence Earth's climate. Understanding their origins and behavior could help us better protect our technology and explore space safely. As we continue to unravel the secrets of cosmic rays, we're reminded of how much we still don't know about the universe. And as we ponder these high-energy particles, we're led to yet another enigma. How do supermassive black holes form, and what role do they play in shaping the cosmos? Now turning to our 18th question, how do supermassive black holes form? These colossal cosmic entities found at the centers of galaxies are millions to billions of times more massive than our Sun. Yet, their origins remain one of the most perplexing mysteries in astrophysics. How do such massive objects come into existence, and how do they grow to such staggering sizes? One leading theory suggests that supermassive black holes form from the remnants of the first stars in the universe. These early stars, known as population 3 stars, were incredibly massive and short-lived. When they died in spectacular supernova explosions, they left behind black holes that could have served as the seeds for supermassive black holes. Over time, these seed black holes could have grown by consuming gas, dust, and even other stars, eventually reaching the enormous sizes we observe today. Another possibility is that supermassive black holes formed directly from the collapse of massive gas clouds in the early universe. These clouds, under the influence of gravity, could have collapsed into black holes without ever forming stars first. This process, known as direct collapse, might explain how supermassive black holes grew so quickly in the universe's infancy. But how exactly this happens and why some black holes grew so much faster than others remains unclear. The growth of supermassive black holes is another area of intense study. As these black holes consume matter, they release enormous amounts of energy, often in the form of powerful jets and radiation. This process, known as accretion, can influence the evolution of entire galaxies. For example, the energy released by a supermassive black hole can heat up surrounding gas, preventing it from cooling and forming new stars. This feedback mechanism plays a crucial role in shaping the structure and growth of galaxies over billions of years. But here's the puzzling part. Some supermassive black holes appear to have existed when the universe was less than 1 billion years old. How did they grow so massive so quickly? This challenges our understanding of black hole formation and growth, as it seems there wasn't enough time for these objects to reach such sizes through normal accretion processes. Could there have been other mechanisms at play, such as mergers between smaller black holes or the existence of even more massive seed black holes? These are questions that continue to baffle scientists. The role of supermassive black holes in galaxy evolution is equally fascinating. Observations show that nearly every large galaxy has a supermassive black hole at its center, suggesting a deep connection between the two. But does the black hole drive the galaxy's evolution, or does the galaxy influence the black hole's growth? Or is it a combination of both? Understanding this relationship is key to unraveling the story of how galaxies, including our own Milky Way, came to be. As we delve deeper into the mysteries of supermassive black holes, we're reminded of how much we still have to learn about the universe's most extreme objects. And as we ponder their origins and growth, we're led to yet another cosmic puzzle. What is the nature of space-time, and how does it shape the fabric of the universe? Now turning to our 19th question, what is the nature of space-time? This invisible fabric, woven together by the forces of gravity, is the very stage on which the universe performs its grand cosmic dance. But what exactly is space-time, and how does it shape the reality we experience? At its core, space-time is a four-dimensional framework that combines the three dimensions of space: length, width, and height, with the dimension of time. This concept, first introduced by Albert Einstein in his theory of general relativity, revolutionized our understanding of gravity. Instead of thinking of gravity as a force pulling objects together, Einstein proposed that massive objects like stars and planets warp the fabric of space-time around them. This curvature dictates how objects move, causing them to follow paths we perceive as gravitational attraction. Imagine space-time as a stretched rubber sheet. Place a heavy ball in the center and the sheet bends, creating a depression. If you roll a smaller ball across the sheet, it will curve toward the heavier object, mimicking the effect of gravity. This simple analogy helps us visualize how massive objects influence the motion of others by distorting space-time. But the nature of space-time goes beyond just curvature. It's also dynamic, capable of stretching, compressing, and even rippling. These ripples, known as gravitational waves, were first detected in 2015, confirming a prediction made by Einstein a century earlier. Gravitational waves are produced by cataclysmic events, such as the collision of black holes or neutron stars, and they carry information about the universe's most violent phenomena. Yet, despite this breakthrough, many questions about space-time remain unanswered. For instance, what is space-time made of? Is it a smooth, continuous fabric, or does it have a granular structure at the smallest scales? Some theories suggest that space-time might be composed of tiny, indivisible units, much like pixels on a screen. This idea, rooted in quantum mechanics, challenges our classical understanding of space-time and hints at a deeper, more fundamental reality. Another mystery is the relationship between space-time and the quantum world. While general relativity describes the behavior of space-time on large scales, quantum mechanics governs the behavior of particles at the smallest scales. These two frameworks, however, are fundamentally incompatible. Reconciling them into a single theory of quantum gravity is one of the greatest challenges in modern physics. Could space-time itself emerge from quantum interactions, or is there a more profound connection waiting to be discovered? And then there's the question of time. Why does it flow in one direction from past to future? Is time an illusion, as some physicists suggest, or is it a fundamental aspect of the universe? The nature of time, intertwined with space, remains one of the most profound mysteries in science. As we explore the fabric of space-time, we're reminded of how much we still don't understand about the universe's underlying structure. And as we ponder these questions, we're led to yet another cosmic enigma. What is the source of ultra-high-energy cosmic rays, and how do they defy our current understanding of physics? Now turning to our 20th question, what is the source of ultra-high-energy cosmic rays? These mysterious particles, traveling through space at nearly the speed of light, carry energies millions of times greater than anything we can produce in our most powerful particle accelerators. Yet, despite decades of study, their origins remain one of the most baffling puzzles in astrophysics. Ultra-high-energy cosmic rays are atomic nuclei, mostly protons, that hurtle through the universe with unimaginable force. When they collide with Earth's atmosphere, they create cascades of secondary particles, which scientists detect using ground-based observatories. But tracing these cosmic rays back to their sources is no easy task. Unlike light, which travels in straight lines, cosmic rays are deflected by magnetic fields as they journey through space, making it nearly impossible to pinpoint where they came from. So, where do these ultra-energetic particles originate? Some theories suggest they might be produced by extreme cosmic events, such as supermassive black holes at the centers of galaxies, or the violent explosions of massive stars known as gamma-ray bursts. Others propose that they could come from even more exotic sources, like the decay of super-heavy particles left over from the early universe. But so far, none of these explanations fully account for the incredible energies these cosmic rays possess. What makes ultra-high-energy cosmic rays even more perplexing is that they seem to defy the limits of our current understanding of physics. According to a phenomenon known as the Greisen-Zatsepin-Kuzmin, or GZK, cutoff, cosmic rays with extremely high energies should lose much of their energy as they travel through the cosmic microwave background radiation, the faint afterglow of the Big Bang. Yet we've detected cosmic rays with energies far beyond this theoretical limit. How are these particles able to reach Earth without losing their energy? Are there unknown processes at work in the universe, or do we need to rethink our understanding of particle physics altogether? The search for answers continues, with scientists using advanced observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah to study these elusive particles. By analyzing their arrival directions and energy levels, researchers hope to uncover clues about their origins and the mechanisms that accelerate them to such extraordinary speeds. But for now, ultra-high-energy cosmic rays remain a tantalizing mystery, challenging our understanding of the universe and pushing the boundaries of science. As we grapple with the enigma of these cosmic particles, we're led to yet another profound question. What is the role of magnetic fields in the universe, and how do they shape the cosmos on both small and large scales? Now turning to our 21st question, what is the role of magnetic fields in the universe? These invisible forces are woven into the fabric of space, shaping the cosmos in ways we are only beginning to understand. From the smallest particles to the largest galaxies, magnetic fields play a crucial role in the behavior and evolution of cosmic structures. Magnetic fields are everywhere in the universe. They thread through galaxies, spiral around stars, and even permeate the vast voids between them. In galaxies, magnetic fields influence the motion of gas and dust, guiding the formation of stars and planets. They can also accelerate charged particles, creating cosmic rays and shaping the structure of interstellar space. But despite their ubiquity, the origins of these magnetic fields remain a mystery. How do they form, and what processes sustain them over billions of years? One of the most intriguing aspects of magnetic fields is their role in star formation. As clouds of gas and dust collapse under gravity, magnetic fields can either help or hinder the process. They can channel material into dense regions, triggering the birth of stars, or they can resist gravitational collapse, slowing down star formation. This delicate balance between magnetism and gravity is still not fully understood, leaving scientists with many questions about how stars come into being. Magnetic fields also play a key role in the behavior of black holes and neutron stars. Around these extreme objects, magnetic fields can become incredibly strong, influencing the flow of matter and energy. For example, the jets of particles ejected from the poles of black holes are thought to be powered by magnetic fields. Similarly, the intense magnetic fields of neutron stars, known as magnetars, can produce some of the most energetic events in the universe, such as gamma-ray bursts. Yet, the mechanisms behind these phenomena are still poorly understood. On a larger scale, magnetic fields shape the structure of galaxies and even the cosmic web, the vast network of filaments that connects galaxies across the universe. They can affect the motion of gas within galaxies, regulate the formation of stars, and even influence the growth of supermassive black holes at their centers. But how do these magnetic fields form in the first place? Are they generated by the motion of charged particles in the early universe, or do they arise from more exotic processes? The study of cosmic magnetic fields is a rapidly evolving field, with new observations and theories emerging all the time. Instruments like the Square Kilometre Array, a next-generation radio telescope, promise to reveal more about the role of magnetic fields in the universe. By mapping these fields across vast distances, scientists hope to uncover their origins and understand how they shape the cosmos. As we explore the influence of magnetic fields, we are reminded of how much we still have to learn about the universe. These invisible forces are a testament to the complexity and beauty of the cosmos, challenging us to rethink our understanding of space and time. And with that, we move to our next question. What is the true nature of gravity, and how does it shape the universe on both the smallest and largest scales? Now turning to our 22nd question, what is the true nature of gravity? This fundamental force governs the motion of planets, stars, and galaxies, yet it remains one of the most profound mysteries in physics. From the apple that inspired Newton to the warping of space-time described by Einstein, our understanding of gravity has evolved dramatically over the centuries. But even today, we are still grappling with its true nature and how it fits into the larger framework of the universe. Gravity, as described by Isaac Newton, is a force that pulls objects toward one another. His law of universal gravitation explained the orbits of planets and the motion of celestial bodies with remarkable precision, but Newton's theory had its limits. It couldn't explain certain anomalies like the slight wobble in Mercury's orbit. Enter Albert Einstein, whose theory of general relativity revolutionized our understanding of gravity. Instead of a force, Einstein described gravity as the curvature of space-time caused by mass and energy. This elegant theory not only explained Mercury's orbit, but also predicted phenomena like black holes and gravitational waves which have since been observed. Yet, even Einstein's theory has its limitations. It breaks down at the smallest scales where the rules of quantum mechanics take over. In the quantum world, particles interact through forces like electromagnetism and the strong and weak nuclear forces, all of which are described by quantum theories. But gravity remains the odd one out. There is no widely accepted quantum theory of gravity, and this gap in our understanding is one of the biggest challenges in modern physics. The quest for a quantum theory of gravity has led to some of the most ambitious ideas in science. One leading candidate is string theory, which proposes that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings could unify all forces, including gravity, into a single framework. Another approach is loop quantum gravity, which suggests that space-time itself is made up of discrete loops. Both theories aim to reconcile gravity with quantum mechanics, but neither has been proven experimentally. The implications of understanding gravity at the quantum level are enormous. It could help us explain the behavior of black holes where gravity becomes incredibly strong, and quantum effects cannot be ignored. It might also shed light on the early universe, where the extreme conditions of the Big Bang require a quantum description of gravity. And it could even reveal new dimensions of space-time hidden from our current understanding. As we continue to explore the true nature of gravity, we are reminded of how much we still have to learn. This force, so familiar yet so mysterious, challenges us to push the boundaries of science and rethink our understanding of the universe. And with that, we move to our next question. What is the origin of cosmic neutrinos, and why are they so difficult to detect and study? Now turning to our 23rd question, what is the origin of cosmic neutrinos? These elusive particles, often called ghost particles, are among the most mysterious and challenging to study in the universe. Neutrinos are tiny, nearly massless particles that rarely interact with matter, making them incredibly difficult to detect. Yet, they are everywhere, streaming through space and even passing through our bodies by the trillions every second without us ever noticing. Cosmic neutrinos are believed to originate from some of the most energetic and violent events in the universe. These include supernova, the explosive deaths of massive stars, as well as the environments around black holes and neutron stars. Even more extreme sources like gamma-ray bursts and the collisions of entire galaxies are thought to produce these ghostly particles. But pinpointing their exact origins is no easy task. Unlike light or other forms of radiation, neutrinos don't follow a straight path and aren't absorbed or deflected by magnetic fields or matter. This means they can travel vast distances across the universe, carrying information from their sources without being altered. Detecting neutrinos is a monumental challenge. Because they interact so weakly with matter, scientists need incredibly sensitive equipment to catch even a handful of them. Massive detectors, often buried deep underground or underwater to shield them from other particles, are used to capture the rare moments when a neutrino collides with an atom. One of the most famous neutrino detectors is the Ice Cube Observatory in Antarctica, which uses a cubic kilometer of ice to detect the faint flashes of light produced when neutrinos interact with the ice. Despite these efforts, the number of cosmic neutrinos detected so far is relatively small, leaving many questions about their origins unanswered. The study of cosmic neutrinos is not just about understanding these particles themselves. It's also about unlocking the secrets of the universe's most extreme environments. Neutrinos can provide clues about the inner workings of supernova, the behavior of matter near black holes, and even the conditions of the early universe. They offer a unique window into processes that are otherwise hidden from our view, making them invaluable to astrophysics. Yet, the mystery of cosmic neutrinos persists. Why do they have such tiny masses? How exactly are they produced in these extreme cosmic events? And what can they tell us about the fundamental laws of physics? These questions drive ongoing research and inspire new technologies to improve our ability to detect and study these ghostly particles. As we continue to explore the origins of cosmic neutrinos, we are reminded of how much we still have to learn about the universe and its most enigmatic inhabitants. And with that, we move to our next question. What is the nature of the Great Attractor, and why does it pull galaxies toward it with such immense force? Now turning to our 24th question, what is the nature of the Great Attractor? This mysterious gravitational anomaly has puzzled scientists for decades, as it exerts an immense pull on galaxies, including our own Milky Way. Located in the direction of the constellations Centaurus and Hydra, the Great Attractor is a region of space that seems to be drawing galaxies toward it at incredible speeds. But what exactly is it, and why is it so difficult to study? The Great Attractor lies about 250 million light-years away from Earth, but its true nature remains shrouded in mystery. One of the biggest challenges in studying it is the fact that it lies behind the plane of our Milky Way galaxy. This region, known as the zone of avoidance, is filled with dense clouds of gas, dust, and stars that block our view of what lies beyond. It's like trying to peer through a thick fog, making it nearly impossible to observe the Great Attractor directly with optical telescopes. Despite these obstacles, scientists have used other methods to study this enigmatic region. By observing the motion of galaxies and measuring their velocities, researchers have deduced that the Great Attractor must be an incredibly massive object or collection of objects. Some theories suggest it could be a supercluster of galaxies, a dense concentration of matter that exerts a strong gravitational pull. Others propose that it might be part of an even larger structure, such as the Laniakea supercluster, which encompasses our own Milky Way and thousands of other galaxies. The Great Attractor's gravitational influence is so powerful that it affects the motion of galaxies across vast distances. This has led scientists to wonder what could be causing such a strong pull. Is it a single massive object like a supermassive black hole, or is it the combined gravity of countless galaxies and dark matter? The answers remain elusive, but the quest to understand the Great Attractor continues to drive advancements in astronomy and cosmology. Studying the Great Attractor is not just about solving a cosmic mystery. It's also about understanding the large-scale structure of the universe and the forces that shape it. By unraveling the secrets of this gravitational anomaly, we can gain insights into how galaxies form, evolve, and move through space. It's a reminder that even in the vastness of the cosmos, there are still phenomena that challenge our understanding and inspire us to explore further. As we continue to probe the nature of the Great Attractor, we are reminded of how much we still have to learn about the universe. And with that, we move to our final question. What lies beyond the observable universe, and what mysteries might be waiting for us in the uncharted regions of space? Now turning to our final question, what lies beyond the observable universe? The observable universe is the portion of the cosmos we can see and study, limited by the distance light has traveled since the Big Bang, approximately 13.8 billion years ago. But what lies beyond this boundary? Is there more to the universe that we simply cannot see, or is this the edge of existence itself? The observable universe is vast, stretching about 93 billion light-years in diameter. Yet, this is just a fraction of what might exist. Beyond this limit, the universe could extend infinitely, filled with galaxies, stars, and planets we may never detect. Alternatively, it might be finite, with boundaries or edges that defy our current understanding of space and time. The truth is, we don't know, and that's what makes this question so fascinating. One of the leading theories about what lies beyond is the concept of the multiverse. This idea suggests that our universe is just one of many, each with its own unique laws of physics and properties. Some multiverse theories propose that these other universes exist in higher dimensions, completely separate from our own. Others suggest they might be bubbles that formed during cosmic inflation, the rapid expansion of the universe just after the Big Bang. While these ideas are compelling, they remain speculative, as we currently have no way to observe or interact with other universes. Another possibility is that the universe is curved in such a way that it loops back on itself. In this scenario, if you could travel far enough in one direction, you might eventually return to your starting point, much like circumnavigating the Earth. However, current observations suggest the universe is flat, meaning it doesn't curve back on itself. Still, this doesn't rule out the existence of unobservable regions beyond our cosmic horizon. Studying what lies beyond the observable universe is incredibly challenging. Since light from these regions hasn't had enough time to reach us, they are, by definition, invisible to our instruments. Even if we could detect faint signals from these distant realms, the expansion of the universe means they are moving away from us faster than the speed of light, making them forever out of reach. Despite these challenges, scientists continue to explore this question through theoretical models and indirect observations. For example, studying the cosmic microwave background radiation, the afterglow of the Big Bang, might provide clues about the universe's geometry and whether there's more beyond what we can see. Additionally, advancements in quantum physics and string theory could one day offer new insights into the nature of reality itself. The mystery of what lies beyond the observable universe reminds us that our understanding of the cosmos is still in its infancy. It's a humbling thought, but also an inspiring one. Every unanswered question is an invitation to explore, to push the boundaries of knowledge, and to uncover the secrets of existence. As we conclude our journey through these 25 unanswered questions about space, we're reminded that the universe is full of wonders waiting to be discovered. Stay curious, keep exploring, and who knows what mysteries we might unravel next. If you enjoyed this cosmic journey, don't forget to like, subscribe, and hit the notification bell for more mind-bending explorations of the universe. Until next time, keep looking up. Now turning to our conclusion, let's take a moment to reflect on the incredible journey we've just taken through the cosmos. From the mysteries of dark matter and dark energy to the enigma of black holes and the search for life beyond Earth, we've explored 25 of the most profound questions about space that still baffle scientists today. Each of these questions reminds us just how much we have yet to discover about the universe. The vastness of our ignorance is not a cause for despair, but rather a source of endless inspiration. Every unanswered question is a doorway to new possibilities, a challenge to our understanding, and an opportunity for future breakthroughs. The universe is a place of infinite wonder, and the more we learn, the more we realize how much remains hidden. As we wrap up this exploration, I encourage you to stay curious. Keep asking questions, keep seeking answers, and keep looking up at the stars. The mysteries of the cosmos are waiting for us to uncover them, and who knows what incredible discoveries lie just beyond the horizon of our current knowledge. If you enjoyed this journey through the unknown, don't forget to share your thoughts in the comments below. What question about space fascinates you the most? And if you want to dive deeper into the wonders of the universe, make sure to like, subscribe, and hit the notification bell so you never miss an update. Until next time, keep exploring, keep wondering, and keep reaching for the stars. The universe is full of secrets, and together we can uncover them one question at a time.